Again, this is just using the previous formula that we had looked at of h over 3 times the top area plus the bottom area times the square root of the top area times the bottom area. Then the weight would be just the density in pounds per cubic foot times the cubic feet, and then we convert that to tons. Calculating excavation volumes and tonnage, we continue with a lot of the same type of dimensions. We have the length is 20 feet, width 30 feet, and its depth is 12 feet. We have a sandy soil, which means it's going to have a friction angle on it, and we're using here a 1 to 2 slope because of its friction angle. Calculate the volume and the weight, which we've already done. We calculated what these numbers would be. Then the next question would be, if your dump truck capacities are 50 tons and payloads are 45 cubic yards, which would be the dump truck capacities, how many truckloads will you need to completely remove the excavated material? Well, of course, what you'll be looking at is volume, and this would be in loose cubic, here's bank cubic yards, and then the weight in tonnage. So take a moment and do that calculation. We can carry 50 tons, or we can carry 45 cubic yards. So which one would control here? Well, the truth is that it's a trick question. And why is it a trick question? Because we only know what the bank cubic yards are. After we excavate material, it becomes loose and its density goes way down because it's a looser material. So our volume goes up. The weight stays the same of our total excavation. Our weight stays the same. It isn't affected, but the material that we remove, because air fills in a lot of these spaces in between the solid particles, our density goes way down, and therefore our volume of material goes up when we remove it from its in situ condition. So the loose cubic yards of the material removed can be much greater than the bank cubic yards, or the volume of the material as it's in place or in situ. It's an example of some of the swell factors for certain types of material. This, of course, is a local property. This is not a universal property. You can't say that all silt has a swell factor of 20%, or clay has a swell factor of 25%, or sand and gravel have swell factors of 50%, and so forth. We have an excavation of highly cohesive clay, which means that we have very high C value when we're looking at the strength of the material. 140 pounds per cubic foot is to be excavated in an urban area. The dimensions of the excavation are something we've looked at before: 20 feet long, 30 feet wide, and 10 feet deep. What is the volume of material? What is the weight of the material to remove? This is an is, not an are. Sorry about that. Volume is 20 times 30 times 10 is 6,000 cubic feet, 222.2 bank cubic yards. The weight is 6,000 cubic feet times 140 pounds per cubic foot, or 420 tons. Knowing that the clay has a swell factor of 25%, what are the volume and tonnage of the material that is actually transported away from the excavation site? So how do we know that the clay has a swell factor of 25%? Well, we just pulled it from this table here. What's this clay 25%? We're using that in this particular example. Again, you can't use that for all clay universally. That value would actually have to be given or determined by your laboratory. So the volume transported is going to be 22.2 bank cubic yards times 125%, or 1.25 loose cubic yards per bank cubic yard, or 277.8 loose cubic yards. This is the amount of material that's actually going to be transported. This is the volume of material transported. The volume of material removed is in bank cubic yards. The volume of material actually transported is loose cubic yards. Again, the weight does not change. The total weight of the soil doesn't change. The soil is less dense and has a lower density, but the total weight is the same. So we'd still be transporting 420 tons of material, but we'll be transporting 277.8 cubic yards of material instead of the 222.2 bank cubic yards. Loading equipment, we'll have a crawler tractor, top loading equipment for loading trucks, front end loaders, front shovels, backhoes, cable operated clamshells, drag lines, conveyor belt loaders fed by bulldozers, and we saw some photos of those or drawings of those earlier. Hauling equipment, we have end dump trucks mounted on a single chassis, but maybe the tractor trailer type, on or off road use, 35 to 85 ton payload capacity, 2,000 pound for 2,000 pound tons. Typically we look at anywhere between 40 and 50 ton payload capacities. Bottom dump trucks are the ones that are dropped at the bottom, much larger, used on construction sites themselves primarily, and so really primarily used on off-road use. Factors affecting equipment selection: type of material to be excavated or hauled, the site conditions, the distance of the haul, time allowed for job completion, and the contract price. These are what affect our equipment selection. Why is it? Let's look at these. Type of material to be excavated and hauled. You know, is it highly cohesive soil, or is it a loose soil like a sand? The site conditions. What are our logistics there? How, you know, is it soil very soft? Can we get heavy equipment in there? Can we not? How far are we going to be hauling the material? If we're hauling it a long way, we're going to want to use hauling equipment or trucks that can move very quickly rather than at a very slow pace. The time allowed for the job completion. Of course, all projects have schedules, and we have to take those things into consideration, and the contract price. So the amount of money, the type of equipment that we put into this project, or in the amount of money we spend on that, it's going to depend on a lot on our schedule and on the contract price. How much money do we have to actually spend to get the job done? For productivity and production, the definition of productivity is going to be output divided by input. We always want our productivity to be positive or greater than 1. If it's not, then we're losing money. So we're here in this particular formula, the production is equal to the machine efficiency times the shrinkage factor for the loose material times the heat capacity of the machine divided by the cycle time of the machine itself. So we have a table here that was developed based on the type of, or actually the volume of the, whatever we're using the dipper to lift the material out. Here again, here's our formula for us to refer to. So the numbers here are the P. So let's say we're moving sand and gravel, and we have 1 cubic yard dipper size. Productivity or production is going to be right at 200 cubic yards per hour. And so this is just a table that's been set up. And of course, it is going to also assume a shrinkage factor here in this for a particular case. Again, we're taking another look at the production formula here. The efficiency factor, E, is the amount of productive time per hour of a piece of equipment. In other words, no equipment is 100% efficient. So crawler tractor equipment is efficient for 50 minutes per hour. Rubber tire hauling units, 45 minutes per hour. Large rubber tired loaders and dozers, 45 minutes per hour. And again, small tired loaders are 50 minutes per hour. So for every hour, these are in production for about 50 minutes and 45 minutes and so forth. So efficiency is the amount of productive time per hour. Heaped capacity comes from the manufacturer. It's the capacity of any type of a dipper or shovel that you pick up, and the heaped portion is that portion that rises above or domes above the device itself, so that actually the amount of material that we're actually removing is greater than the volume of the dipper itself. Shrinkage factor is sort of an inverse of the swell factor. We can determine the swell factor. Then our shrinkage factor is going to be sort of the inverse of our swell factor. So it's here's our formula for determining the shrinkage factor for the loose material. Cycle time. The cycle time is a combination of travel time and also the fixed time. This is not CT, this should be CF. So the travel time is determined by this formula, the distance divided by the speed in miles per hour, times this conversion factor, which converts feet per minute from 1 mile per hour. So 88 feet per minute is the same as traveling 1 mile per hour. So you can see the distance is going to have a lot to do with the travel time that we're using. The travel time is a variable based on the project. The fixed time is a function of the material. Of the equipment itself, and it's determined by the manufacturer. So what really affects the production here is going to be our travel time, because the distance and the speed that we're using, and the speed, of course, is a function of the equipment itself, the load on the equipment, and also the type of surface that the equipment is actually traveling across. So as our travel time goes up, our C is going to get larger, and the denominator gets larger, and what happens to our production? Our production goes down. Here's an example, a crawler-mounted power shovel. H is equal to 2 cubic yards. That's our heap capacity. Having a 1 1/2 cubic yard bucket is to load well-blasted rock into trucks. The machine efficiency is 50 minutes per hour. What is the total cycle time? Well, the shrinkage factor for this is the swell we're using is 50% for this type of material, the blasted rock. So we determine our shrinkage factor is 0.67. Okay, and based on table 3.2 above, which we looked at earlier, our production will be 180 cubic yards. We're looking at the total cycle time here based on this particular equation. The cycle time then is equal to the efficiency times the shrinkage factor times the heap capacity divided by the production. So efficiency is 50 times 0.67 times 2, which is heap capacity, divided by 180. So our cycle time is going to be 0.372 to get the production of 180 cubic yards. An in-class problem, a rubber-tired scraper with a heaped capacity of 30 cubic yards has a cycle fixed time of 1 minute, loading, dumping, and turning. The average speed of the scraper is 3.5 miles per hour, and it must travel at 0.75 miles round trip. Calculate the anticipated production of the machine if it is hauling clay with a swell factor of 25%. Assume a machine efficiency of 50 minutes per hour. The cycle fixed time cycle means we at a point where we scoop it up, and then the machine will turn, dump it into the truck, and then go back to the point where it's about to scoop it up again. That would be an example of the cycle fixed time. 1 minute to accomplish that. So we have, we're looking at the anticipated production of the machine. We know that the scraper is going to move at 3.5 miles per hour. We have a swell factor of 25%. So from this, we can calculate the I value from using 3.5 miles. The 25% factor, which is our shrinkage factor. A shrinkage factor would be 1 over 1 plus 25 over 100, or 1 over 1.25. So that would be our shrinkage factor. Assume a machine efficiency of 50. So to calculate our production, we'll have to go we do have 50. We calculate 1 over 1.25. And we calculate our travel time, 3.5 miles per hour, and our distance is 0.75 miles. And it will convert that to feet per minute from miles per hour, and that would give us our cycle time, our travel cycle time, and then our fixed cycle time would be 1 minute. So you put that into our formula here. Cycle time is a distance, it's 0.75 times 5,280 feet per mile. Traveling at 0.75 miles per hour. 0.75 miles times 5,280 feet per mile, which would give us the distance in feet. That's traveling at 3.5 miles per hour times 88 feet per minute per mile per hour. That would give us this total time here of 12.9 minutes. 12.9 minutes plus the fixed time of 1 gives us 13.9 minutes. Our shrinkage factor is going to be 1 divided by 1.25, or 0.8. So our production is going to be 50 times 0.8, which is our shrinkage factor, times 30, which is our heap capacity, and divided by our cycle time. So the production will be 86.3 cubic yards per hour in bank, meaning in bank soil. Basic considerations of load and haul operations. The average haul amount in tons, convertible to volume, bank cubic yards. Haul road length and profile, the length and grade of the haul. Road grade resistance, positive grade versus negative grade. In vertical, divided by the ratio of vertical to horizontal in percentage. Be rise over the distance in height over the horizontal distance. The rolling resistance, the flexing of rise over run is what I was looking for, rise over run. Rolling resistance is going to be flexing of the tires and the roadway surface deformation, which is going to have an impact on the speed that our equipment can actually travel. Total load haul resistance, THHR in percentage, is equal to the grade resistance in percentage plus the rolling resistance in pounds per ton divided by 20. Example, on a single segment, grade resistance equals to plus 3.5%. The rolling resistance is 100 pounds per ton. So 3.5 plus 100 divided by 20 is equal to 8.5%. And this is 20 because it's really 2,000 and the whole thing is times 100%. So that's how we get our percentage on there. It's 100 over 20 times 100%. So it'd be the same as 100 divided by 2,000 times 100% is what this is, 100 over 20. THRR, is used to calculate the travel time for each segment of a haul so that the travel time can be estimated for daily production. Total haul road resistance example. A dump truck hauls excavated material over a segment of loose sand roadway with a grade of 6%. What is the total haul road resistance for this segment? The rolling resistance values of, if it's a hard, smooth surface, is 40 pounds per ton. A dirt roadway, rutted, flexing under the load, 100 pounds per ton. A rutted dirt roadway, soft under travel. No maintenance, no stabilization, 150 pounds per ton. Loose sand and gravel, 20 pounds per 200 pounds per ton, and a soft, muddy, rutted roadway, no maintenance, tire penetration of over 6 inches is equivalent to 200 to 400 pounds per ton of rolling resistance. Truck load and haul analysis. It's based on the truck payload in bank cubic yards, or the truck rated capacity in tons, or its equivalent in cubic yards. Based on weight, in situ material weight, pounds per bank cubic yard, the bank cubic yards per loader bucket, rated bucket size, the material swell, the bucket fill factor, the truck load time in minutes, the loader cycle time in minutes, and then the truck spot and maneuver time in minutes. Truckload haul and analysis, the truck payload, the quantity of material in bank cubic yards moved in one complete truck haul cycle. The truck rated capacity is the weight of the bank material to be hauled. In situ material weight in pounds per bank cubic yard, the unit weight of material being moved, including the weight of any natural moisture content. Bank cubic yards per loader bucket, content of average bank cubic yards of the bucket of the loading equipment in one loader bucket cycle. The rated bucket size, manufacturer's rated heat capacity in cubic yards of the bucket being used. Truck load and haul analysis is an example. Caterpillar rates its 773B end dump truck at 50 tons payload capacity, and the volumetric capacity heaped at 2-to-1 slopes as 44.6 cubic yards. If a material with an in-situ weight of 3,200 pounds per bank cubic yard, which is our unit weight, and a swell factor of 30% were being hauled, the truck payload capacity based on weight would be 50 tons times 2,000 pounds per ton, divided by 3,200 pounds per bank cubic yard, which is our density, which means that we could have 31.3 loose cubic yards in the back of the truck if it could hold 50 tons. So this would be 3,200 pounds of cubic yards of material per bank cubic yard. The truck capacity based on volume would be 44.6 bank cubic yards times our swell factor plus 1.30 linear cubic yards per bank cubic yards, would come up with 34.3 linear cubic yards. Which one controls and why? Let you answer that question. Here's another example. Same truck. This time it has a 50 tons payload capacity and volume capacity of 44.6 cubic yards. The material has an in-situ weight of 2,200 pounds per bank cubic yard, which is a much lower density than the one before, and a swell factor of only 15% being hauled. The truck payload capacity based on weight would be 50 times 2,000 pounds per ton times 2,200 pounds per bank cubic yard, be 45.5 linear cubic yards based on tonnage. The truck capacity based on volume would be 44.6 bank cubic yards times 1.15 linear cubic yards per bank cubic yards. I'm sorry, loose cubic yards per bank cubic yard, not linear, loose cubic yards, is equal to 38.8 loose cubic yards. Again, which one controls? In this particular case, the payload capacity based on weight is 45.5. The truck volume would be 38.8. So its volume capacity is 38.8 loose cubic yards, whereas the weight capacity is 45.5 cubic yards. So really what controls is the one with the least. Okay? So its least capacity is 38.8. So really it's only going to carry 38.8 linear loose cubic yards. It will not be able to haul 50 tons of material. And this one before, what do we see differently here? Well, we see a much lower density and a much smaller swell factor. Example 2, a sandy soil was with an in-place density of 120 pounds per cubic foot is to be excavated with a 1-to-2 slope on the sides. The dimensions of the excavation are 20, length, width 30, and the depth 12. So we have slopes on the side. What are the volume of material to be removed? What is the weight of material to be removed? Well, the volume, this is the same one we looked at earlier, is going to be equal to h over 3 times the top area plus the bottom area plus the square root of the top area times the bottom area. The top area is 20 times 30, 20 times 30, 600 square feet. The bottom area is going to be using the formula 20 minus 12 over 2 times 2 times 30 minus 12 over 2 times 2 is equal to 8 times 18, 144 cubic feet. So our volume is going to be 153.8 cubic yards, bank cubic yards. The weight is going to be 4151.76 times 120 pounds per cubic foot. Pounds times 120 pounds per cubic foot is equal to 498. Let's back this up again. 4,151.76 cubic feet times 120 pounds per cubic feet, pounds per cubic foot is going to give us 200,212 pounds, or 249.1 tons. And one of the things I really want to point out here is that the question asks you how much is going to be removed. They're referring to bank cubic yards. We're talking about removal. You can see down here we didn't do any correction factors as far as dealing with swell, no swell factors. So we're dealing with bank cubic yards. How much is to be removed? The other question is how much to be transported, or how many trucks will be required. Then you look at loose cubic yards, and we take into account the swell factor on the volume only. The swell factor does not affect the total weight. Example 2, a sandy soil with an in-place density of 120 pounds per cubic foot is to be excavated with a 1-to-2 slope on the sides. The dimensions of the excavation are 20 by 30 by 12. What is the volume of material to be removed, and what is the weight of the material to be removed? Again, we come up with the same numbers that we had calculated earlier, because what I wanted to do was to give you another dimension to the question. Remember, we says how much will be removed. Now we're asking how many trucks are going to be necessary to remove the material, or to transport the material. This first part of the question is about how much is to be removed, which refers to bank cubic yards. The next one is how much is to be transported, and how many trucks do we need, which would be loose cubic yards. So here we have a truck capacities are 50 tons and or 45 cubic yards. How many trucks do we need? Well, based on volume times our swell factor, divided by the capacity of each truck, we would need 5.12 trucks. Can't use a 12 100ths of a truck, so we would round it up to 6 truckloads. Based on weight, we'd use 249.1 tons divided by 50 tons per truck, or 4.985 truckloads. So how many trucks will we need to transport this amount of material? And that would be 6 truckloads. We could not transport it in 5 because it would not be weight limited. It would in fact be volume limited because of the swell factor being so large, actually, 50%. Truck load and haul analysis, the bucket fill factor, a dimensionless factor representing the decimal equivalent of the percentage of full rated bucket capacity that on the average will be retained in the bucket for each load cycle. The truck load time, the time duration in minutes that on the average is required to fill a truck with a single payload quantity. The loader cycle time in minutes, time duration in minutes that on the average is required for the loader to complete one loader bucket cycle measured from the point in time at which the loader dumps its contents into the truck, moves back to the material being loaded, obtained another bucket of material, moves back to the truck, and completes the dumping of the material into the truck. So the loader cycle time is from point A to point B and all the way back to point A. Truck spot and maneuver time, time duration in minutes that on the average is required for a truck when loaded to pull out of the loading location to the start of the haul route and for the next truck to pull into the loading position. Again, here's our analysis using our shrinkage factor and the volume of the bucket size, the truck payloads in bank cubic yards, and then the truck load time, the amount of time it takes to actually load the truck and to get it, use the spot time on the truck. So this is the relationship for determining of truck load time. How much material, how many buckets do we need to fill it, and then the time for that loader to reach its cycle time. Material swells, the percentage of volume increase when this material being moved is loosened from the in situ density to the lower density of the loose material during loading operations. Again, we looked at swell percentage times. Again, the swell is the inverse of the shrinkage factor, pretty much. And so, again, these are based on local conditions. These are not universal swell values. Another table which includes the truck load and haul analysis, the cycle time, the number of trucks to balance the loader, the truck unit productivity in bank cubic yards per hour, and the truck spread productivity in bank cubic yards per hour. Relationships for determining of truck loader, haul unit, and spread productivity. Okay, if you look at the cycle times, the truck load time in minutes, plus the loader travel time in minutes, plus the turn and dump time in minutes, plus the return travel time. Again, from point A back to point A. Number of trucks to balance the loader. We have to have trucks waiting to pull up when the first truck leaves. The next truck has to pull in, and so that it can fill it. So if we're traveling a long distance to unload it, the turn and dump time, then we're going to need more trucks to keep our balance so that the loader isn't sitting idle and we don't have too many trucks sitting idle. Example 7, a 130-ton bottom dump haul unit loaded by a 15 cubic yard front end loader moving common excavation on 20,457 feet one-way haul in situ weight of the material including moisture is 2,850 pounds per bank cubic yard. Now this is pounds per bank cubic yard, not pounds per cubic foot. And assumed bucket factor and time duration constants. Haul unit productivity, P is equal to 177 bank cubic yards per hour, and the spread productivity using 6 haul units was 1,062 bank cubic yards per hour. This is a computer-generated, basically a spreadsheet that was used where they put in the formulas and pull the values down and come up with our productivity, our production rates. Rock in situ unit weight, 4,400 pounds per bank cubic yard. A swell factor of 60%. Other variables may be assumed. Again, here we're getting the production is given to us from the table, and then we're looking at the haul times or the cycle times for these particular units that are necessary to achieve that the production that's desired. We have a very long 11,900 foot one-way haul. It means we'll have to have a lot of trucks available in order to balance the amount of material being removed with the amount of material being hauled. When we do excavations, we have to protect them, taking steps to ensure that the sidewall cave-ins do not occur, which can lead to injury or death to workers, damage to farms and equipment, and costly removal of caved earth. The amount of protection required depends on the depth of the excavation, the soil type, meaning is it cohesive, is it non-cohesive, what is the friction factor for that particular material, the level of the water table, the type of foundation to be built, and the available space for excavations. Especially for less stable soils, the slope, the sides to angle of repose are greater, is space limited. So we have less stable soils, we of course want to have a much lower rise over run or vertical over horizontal slope, as opposed to one where we can have maybe a 1 to 2 slope. We'd want something much smaller if we have less stable soils. The temporary support of excavated walls, we'd have to support them temporarily. And an example of that would be interlocking sheet piles, which we see a lot of down here, particularly on vertical construction when we're excavating the foundations. The interlocking sheet piles can be used for a couple of things. One, to hold the side walls of the excavation in place, but also can be used as a means of a water barrier. And any questions, again, write down any questions. We can talk about these when we come back when I come back to class next week. We can review some of this if you choose to. It's a lot of material. I presented very quickly. It'd be a much slower presentation in class because you would have the opportunity, of course, to interrupt me. But we don't have that luxury today, and the assumption is you get it all and you understand it all. You will have to look at this. There are a lot of vocabulary in here. There's some formulas, and so you should look at these. And any formulas that may be required on the exam, I will give to you. You won't have to memorize them. Any tables that might be required, such as swell, you won't have to memorize. I will give you those. The important thing is that you understand the concept of doing these calculations. Now, as far as the volume, for excavation and fill, those are formulas that are easy to remember. They're commonsensical. You will not be given those formulas, but as far as the formulas for production and so forth, I will give you those formulas. So again, if you have any questions, write them down. You can have me review this over and over and over again. You guys who are in feeds, you won't be having a feeds presentation. This is your presentation in lieu of a feeds presentation. So anyway, thank you. Hope you enjoyed these 2 presentations for today. And when we get back, we'll move on to other things. Thank you.